Okay, so when we're referring to sound intensity, it's going to go back to this idea from this, not that figure. Oh, now look, I'm not going to be able to find it. That's the speed. Oh, here it is. All right. This table from your textbook, which shows sound intensity level beta and intensity I. So intensity is described in two ways, and you have both of these formulas on your formula page. The equation for beta is tricky. It's got some unusual things in it. The letter I is in there, so we can use I for intensity or beta for intensity. Beta is in decibels, and that's a more traditional measure. It's easier for our brains to kind of wrap around, so that's why we use that other scale. As far as the formulas for this, we're going to be practicing these over the next 20 minutes or so, but I just want to show you where they are on your equation page. This very last little 3 lines of this unit. It says sound. It doesn't even call it intensity, right? So we just need to know. I stands for intensity, P stands for power. I know P stands for power because the units are listed as watts per square meter, and watts is the correct unit for power. So power per unit area. They also list this I0, which is also not labeled, but it's there. That's the threshold of hearing. And that's an important number. We're going to use that number to calculate the number of decibels, because I0 shows up in this formula for beta. And then we'll also be practicing the spherical waves equation. I want to describe why that equation exists, why it is the way it is, and show how it's used. These are relatively straightforward physics ideas once you see them, but the math or algebra behind them is a little tricky. So they're important to practice. I would not be surprised to see an intensity question on the exam. So probably a good idea to get good at it. These are questions 3 and 4 in, let's see if I can figure out where I stuck them over here, it looks like. These are questions 3 and 4 from your quest. I'll be starting with question 4. I think it's a little more straightforward, and it gets to the point of decibels. So I'm just going to use this example from the one I pulled. If you've not done questions 3 and 4 in your quest, this is a great time to try to knock those out and see if you can get them correct. We can do it all together. I can help you. We can make sure you've got at least those 2 problems done. All right, so what's happening here is they have one person singing. The number of decibels is 73.6 decibels. What would be the sound level produced by a chorus of 25 of the same type singer, all singing in the same intensity? They want the answer in decibels. So we know that 25 more means the intensity goes up by 24, but that's not the number of decimals going up by 25, but that would be the intensity as power per area. The I would be going up by a factor of 25. So the first step is to convert the number of decibels into intensity. That's job number 1. Once I have that intensity, I'm going to multiply that intensity by 25 to get a new intensity. I'm going to call it I prime. Then I'm going to use that I prime to calculate beta, which is the number of decibels. That's a new number of decibels, right? So we started out with a number of decibels that's given to us. We're going to change that to intensity. Because the intensity is what goes up by 25, the letter I goes up by 25, not the letter beta. It's a little tricky. It's important to know that it'd be easy enough just to multiply 73.6 by 25, but that's way off the scale for that anyway. That doesn't happen. It goes up to about 120, and that's at, basically your ears are going to explode. All right, so let's give this a try. We're starting with 73.6 decibels. And again, this math is a little bit tricky. We're not used to using logs very much. So I want to use this to find out what I is. The formula for beta includes I, it's 10 times log base 10 of I over I naught, or I 0. Just as a side note, I can make a note to myself here, I 0 is equal to 10 to the minus 12 watts per square meter. That's a number we'll need to know. There's a couple of approaches here. I could go ahead and plug the numbers in and then solve it, or I could solve this for I ahead of time and then substitute in the values. I'm going to choose the latter of those because I think it will be a little more clear. So if I want to get, I'm trying to get what I is all by itself. So the first step, I have 10 times log. I'm going to be dividing both sides by 10. So let's do that first. So that would mean I have beta over 10 equals log base 10 of I over I naught. How did we get rid of a log? I don't know, where do we learn this? Do we learn this in algebra? If something's inside a log and I want to expose it,
Find the exponent.
find the exponent, right. But I'm just curious, where do we learn to do that? I'm just curious. Is that like algebra 1, algebra 2? Algebra 2 maybe? Okay. Well, we're learning it now, either way. Good job, Jack. So, this is a log base 10, so that base is what is going to be the base term that will have a new exponent. So to get both sides, to get that log base 10 clear, I'm going to take the number 10 and raise it to this power 10 raised to the beta over 10, and that's equal to I over I naught. That clears out the log. And then to get I by itself, I multiply this by I naught. So I naught times 10, that 10 is raised to the power beta over 10, and that will finally give me back I. You have to wrestle around with that formula a lot, right? That's not an easy solution. I'm just going to plug all the values in on this other side of I, since I know what those all need to be. This is going to be 10 to the negative 12 times 10 raised to the beta over 10. Beta is 73.6, and I'm dividing 73.6 by 10. So that would be 10 raised to the negative 12 power times 10 raised to the 7.36 power. And another trick you can play with exponents is you can, if they have the same base, you can add the exponents together. So I could add negative 12 to 7.36. That would be 10 raised to the 4.64, negative 4.64, I think. That's I. You could also write that in scientific notation. And if I had my calculator, I could do that lickety split. Here we go. Negative 4.64. Your answers, of course, will be slightly different depending on what numbers you're given in your problem. So here's 2.29 times 10 to the minus 5 watts per meter squared. That's a lot of work to find out what the intensity was, even though they told us what the intensity was, right? They told us the number of decibels, but we had to change it to I. So now we need to multiply I by 25, because now there's 25 singers instead of 1. So I just multiply that by 25 on my calculator, and I get 5.727 times 10 to the negative 4 watts per meter squared. And now I need to convert that, what I'm calling I prime, to beta prime, which is going to be 10 log base 10 of that new I over the original, or that over that I naught. So I've got to plug it back into this equation to get decibels back out. So I've got to wrestle with that equation forward and backward. 10 times log base 10 of the new I, which is 5.727 times 10 to the minus 4 over 10 to the minus 12. I naught is always the same number. It's always the threshold of hearing, 10 to the minus 12. And let's see if I can get a result of this. Uh, 5.727 10 to the negative 4 divided by 10 to the negative 12. Let's see if I did that all right. Okay, so this gives me a value of I as 87.6 decibels. My reference for that is, I know it needed to be more than the original number of decibels. If it was 10 times more intensity, the number would have increased just by 10. I would have just gone from 73.6 to 83.6, add 10 to it. If I'd added 100, I would be adding 20. If I multiplied it by 100, I'd be adding 20. So it's going to be somewhere between adding 10 and adding 20. I can help you sort of with that little figuring going on if you want, but this is the kind of change we would expect for this. So what I would encourage you right now is, we've got a little bit of slack time here. I'm going to take probably about 10 minutes to do the next problem also. So I'm going to give you 3 or 4 minutes just to kind of try to work through that on your own for your own quest problem. Many of you probably have already done the quest and don't even need to worry about this anymore, but it might not be a bad idea to try it again with this approach. I'm going to leave this up here and let you all play around with that for a few minutes. Then we go back to sort of the thought process at the beginning, and then I can scroll down to whatever else you might need on there if you need to. It's going to see, maybe if nobody's working on it, we can go ahead right away, but I have a feeling a lot of folks already did it. All right, well, I'm going to go ahead and approach this next question, number 3. If you're still working on question 4, let me know, and I'd be happy to try to help with that a little bit. There should be a little bit of time reserved here at the end to work on one or the other if you still need that. Okay, so question number 3. We've got to kind of play the same game with this. They give me an intensity in decibels, and they ask how far away I would need to be for that to be barely audible. We know that the barely audible is I0 or I0. But this involves something like distance, which we haven't played around with yet, right? But I think you understand in general, the farther away you are from whatever is making sound, the less intense it is, right? The lower the volume, if you will. So that 3.9 meters matters, and the question is how far away would we have to be for that intensity in decibels to go down to 0? We're trying for 0 decibels. The intensity they're looking for is 10 to the minus 12. And if I plug in the intensity of barely being able to hear, this equates to 0 decibels. So this is what the question is asking. Where does that happen? Let's sort of think conceptually about what something that's making sound, right? Like me. So I'm up here talking, and my voice is spreading out in all directions. It's kind of collimated a bit toward the direction I'm facing, but we're going to think a little more generally about it because it makes the analysis easier. We're think about it spreading out in terms of a sphere, a hollow sphere. So imagine a hollow sphere of sound extending out, and the farther away we get, the bigger that area, right? And if we think back, area, the word area is important here because if you think back from the definition of intensity, it's power divided by area. So if my voice has a unique power that's always there, the intensity will change as a result of how big the area is that power is getting spread out over. How big is the area my voice is getting spread out over? And if we're using this as a sphere, that's going to be power over the area of a sphere. And a few of you might have in your head what the formula is for the area of a sphere. You don't have to remember it because it's in the formula. There's all these things floating around in your head, right? Like we've got pi r squared, 2 pi r, what's 4/3 pi r cubed? These are all volumes or areas of circles or spheres. Does anybody remember what the area of a sphere is, the outside area, what that formula might be? It's locked away somewhere. I'm sure at some point you probably had to learn it. As part of this formula that's given, it's the very last formula on your formula page for this unit. It's P over 4 pi r squared. 4 pi r squared is the area of a sphere. So if I know how far away somebody's listening, I can calculate the area that power has been distributed over. So if you are 5 meters away, I can calculate the area of a sphere with a 5-meter radius, because I'm thinking my voice is spreading out as a big sphere, but the power stays the same. So for this one, power is going to be staying the same. So let's write a process or procedure for this. So I'm going to take power. I need to figure out what the power is based on the number of decibels. So I've got to get from decibels to power. But before I can do power, I actually have to calculate the intensity and then use the formula, the given area at that 3.9 meters to figure out what the power is. And then I'm going to use the power to calculate the new intensity. I'm going to set the new intensity equal to I naught and solve for the distance away, solve for R. I'm going to go through that process with you. Let me shrink this down a little bit. I'll keep that little note up to the top here. And let's give this a try based on the numbers that they gave us. 36.6 and 3.9. Okay. Not that matters too much. Everybody's is a little different. So the number of decibels for this is 36.6. I'm going to use that to calculate the intensity. The intensity, remember, is calculated as 10 to the minus 12 times 10 raised to the beta over 10 power. We derived this equation a little bit earlier. So that's 10 to the negative 12 times 10. This is 36.6 over 10. So that's 10 to the minus 12 times 10 to the 3.66. Somebody's got really sloppy handwriting up here. 3.66 So my original intensity is 8.34, sorry, 10 to the negative 8.34, I think. 10 to the negative 8.34, if I'm doing the math right there. And that's equal to power over area. And the area can be figured out using the area of a sphere. It's a lot of steps here. Power over area of a sphere, which is 4 pi r squared. They give me r equals 3.9 meters, I think, in my example. Doesn't really matter, whatever you're plugging in there from your problem. So I could use that to solve for P. P equals 4 pi times 3.9 meters squared times 10 to the negative 8.34. I just rearrange this equation by multiplying both sides by this area. That's the area term. It's all numbers there, so I can actually get a power. That's the power that's constant throughout the problem. It's important to get the power because now I'm going to use that power to figure out what the area has to be for a new or different intensity that's been listed. There's a lot going on here math-wise, but conceptually, the idea is my voice, for example, has the same power no matter what. The intensity will change based on how far away you are. The way to figure that out is to use the area of a sphere, which is 4 pi r squared. So I spent this whole first part of the problem figuring out what that power is. I was told decibels. From decibels, I calculate intensity. From intensity, I calculate power. So the power value is listed right here. This is what we're going to find next. That's a lot of numbers. 4 pi times 3.9 squared times 10 raised to the negative 8.34 power. And this is going to be the power 8.737 times 10 to the negative 7 watts. That's an important number for me to know what the power is. I can use the power to calculate intensity if I know area. Intensity equals power over area. Or if I know what the intensity is, I could use this to calculate the area. So that's what I'm going to do. I'm going to rearrange this equation to solve for area. Area equals power over intensity. They want me to set the intensity equal to I naught. Where can I barely hear this? How far away do I need to be? So I have my 4 pi r squared equals the power, which I already calculated, 8.737, 10 to the minus 7 watts, divided by the new intensity, which is 10 to the minus 12 watts per meter squared. My units will come out to be meters squared, so that's good. So I find out that 4 pi r squared equals, if I take that fraction, I get 873,653 square meters. I can go back and solve that for r, divide both sides by 4 pi and take the square root. So square root of that divided by 4 pi. Let's see, this number makes sense. I think I have r equals 828 meters. So we'd have a distance of 828 meters, which is almost a kilometer. That would be barely audible to the average human. Seems a lot farther than I was expecting, to be honest. So I'm not sure I calculated everything exactly right, but I think I got it. Looks okay, unless I'm just going to try one more thing just to double check my answer. Yeah, the way I entered it on my calculator, I think I put the pi on the wrong side of the equation, so that number was bigger than I expected. This is actually only 264 meters. But again, it doesn't really matter, because you're gonna have different numbers anyway. The math that's written up there is the way to go with it. I know it's not the most exciting or interesting thing to watch Dr. Scheer come up here and do physics and math, so I do this rarely, but I think in this case it's important. We haven't been over how to do intensity much. That formula for decibels is really weird, unusual, something we're not used to. We have to practice it. So that's why I've got all that up here. That leaves us about 5 minutes. I'll give you a couple reminders and let you continue your work. And then if you have any questions, I can try to help you with it. The reminders are post-lab conclusion due Thursday, if you did the lab. When we get back from break, that first day I see you, bright and early Tuesday morning, we'll have our Unit 17 exam. Then we'll be beginning content for Unit 8. The last thing is that Quest assignment number 2 is due tonight. The current Unit 7, Quest 2 due tonight. After tonight, I will make sure that the solutions are available to both Quest assignments so that you can use those to make your custom review. But if you do notice something that maybe I forgot to do that, because shocker, I do forget to do things like set dates, you're welcome to send me a reminder either on Focus or via email. I will have my computer at home and be checking that periodically over break, so if you have any questions,